Hi, today's topic is inverse functions, as you can see, and I have a pair of inverse functions here. The one on the left takes Celsius degrees as input and turns them to Fahrenheit degrees. So if you knew that it was, say, 100 degrees Celsius, you put the 100 in for X, you do the work, and it would get us to a Fahrenheit temperature of the boiling point of water, since 100 is the boiling point in Celsius. The other formula, on the other hand, its input is Fahrenheit degrees, so this one would take, say, 32 degrees Fahrenheit and turn it into 0 degrees Celsius, since that's the freezing temperature of water. These guys are, you probably have seen these two before, and when we talk about inverses, this is a common topic to address because we're somewhat familiar with transferring between Celsius and Fahrenheit. So the deal with a function and its inverse is that they undo each other. In simplest terms, they undo each other. Now, you've studied or you've taken inverse functions before. Today we're going to today we are going to begin showing you a way to determine if two functions are inverses. And I'm going to ask you first, we're going to do the composition f of c of x. We're using the two functions on top, and you'll remember that the second goes into the first. So this business is all going to become x over here. So the f function is 9/5 x. Well, this time we're using is x. 5/9 times x minus 32. And then the rest of this said add 32. And let's do a little arithmetic. Everything here is hooked with multiply, so it makes no difference if we do these two things first, which would make sense because you can see 9/5 times 5/9 is 1, or those things cancel out. That's leaving us with x minus 32 plus 32, which is equal to x. And hey, that's kind of neat. When we composed f of c of x, it all boiled down to x. Now I'd like you to practice a little bit more composing. This time we want to go the opposite direction. So we want to put the f function, all this business, in place of that x and work it out. I'm going to ask you to pause the video and do that right now. Here's my work for that computation. 5/9 comes from this formula. That's the c function. We're going to do that to x, which is the f function, x minus 32. Inside the brackets, plus 32 minus 32 is 0, so this comes down to 5/9 times 9/5 x. Again, that cancels and we get x, and what you've just noticed is true. This is a process that we can use to tell whether two functions are inverses. You compose both ways. So if you compose both ways, inverse functions simplify to x. If you've done the simplification and you don't get x, that means they're not inverses of each other. But if two functions are inverses, if you compose both ways, you should simplify to only x, which is kind of cool, really. Our first activity let us verify to see if two functions were inverses. Now we want to talk about how you can find the inverse of a function if it's written in equation form, if it's in a graph, or a table of values. So in an equation form, what you do, the rule says switch x and y, switch x with y, and solve for the new y. So if I were going to apply that here, remembering that f of x stands for y, here comes my work. I switch x and y, so it's going to say x is equal to 4y cubed minus 1. I solve for the new y. That means I got to add 1 to both sides to start with. Trying to get y by itself, I divide by 4. X plus 1 over 4 is equal to y cubed. I don't want y cubed, I want y. So y will equal the cube root of x plus 1 all over 4. This is the inverse function of the one that we were given, and you can see that this one had a cubed, this has a cubed root, this had minus 1, this has plus 1, this had times 4, this has divide by 4. So these guys are inverses of each other. The rule says switch x and y, solve for the new y. If you're in a table or graph, to get the inverse function, you switch x with y. And I'd like us to see that here for just a second. If our function is 2x minus 1, we can set up a table of values there using, which most of us do, -2 to 2. You could use other values, it doesn't matter, but those will work good here in our graph square. When x is -2 in this thing, 2 times -2 is -4, minus 1 is -5. And I'm going to ask you to go ahead and figure the rest of these, and I'll do that as well. Okay, here are my results, and that is the line 2x minus 1. Let's go ahead and plot those things. -2 and -5 down here, -1 and -3, 0 and -1, 1 and 1, and finally 2 and 3. So that line goes right through there. Now, according to this, to find the inverse, you switch x with y. So if these now become our inputs, okay, this is going to be in my inverse, that's the input, this is the output. And I can find the output just by switching. So if x is -5, y will be -2. And this function will be the inverse of the original line. So now let's plot -5 and -2. That's right here. -3 and -1 right here. -1 and 0. 1 and 1. Oh, that was on both. 3 and 2. And so our inverse function is a line that looks like this. And I would love to have you notice this. The graphs of the function and its inverse are a reflection. Okay? They reflect each other over the line y equals x. And that's the diagonal line that goes through 0 and all the way up. The red graph is a reflection of the black over that line, and that will always be true because you've switched x with y. Alright, let's move on. I have a problem that I would like to have you solve. We're going to ask you to graph a function along with its inverse. So will you pause the video, please? I'm going to use as inputs my same -2 to 2, and let's figure out what the graph and its inverse look like. Here are my results. I used my -2 to 2 as x as input into this, 1/2 x squared, got the fat parabola. Then the inverse of that would be to switch x and y from this function. So my red graph is the inverse. The question here, is f inverse a function? And ladies and gentlemen, we know it can't be. It does not pass the vertical line test because there are lines that will hit that red graph more than once. This is no. And again, the reasoning, it doesn't pass the vertical line test. That's from the graph. From the table, you can also answer no, because we see right here we have repeated x's. They're not always with the same y. A repeated x isn't with the same y. So we can't say that that red is a function. However, if we want to ensure that the inverse will produce a function, we limit the domain on the original function. Limit the domain on f of x. In fact, as you look at this, our problem occurs because we have this negative branch. So if we restrict the domain on f of x to positive values only, okay? So for this example, if the domain were positive only, then we would have a function, because all we'd get is this part and this part. I'm going to outline those both in black. Restricting the domain to only positives would give us this branch of the parabola and this branch. That can be a function, right? And we got that by limiting the domain on the original. So as we said, if we limit that domain to only positive x, then we get a function in the inverse. Okay, here's the big thing. Let's do all of it together. We want to find the inverse of a function, verify by composition that they are inverses, graph the function and its inverse, and determine if the inverse is a function. I'm going to ask you now to pause the video. We're going to do each of these parts, and then I'll explain my responses to each. Alright, here are my thoughts. I'll tell you, this was a lot of work to do on your own, but it really does encompass everything that we are supposed to do. Started out by finding the inverse of the function, switching x with y, solving for the new y. So my inverse function, I'm going to call it g of x here, is x minus 2 divided by negative 3. To verify that those two, f and g, are inverses, we compose them both ways. F of g of x, so I'm putting the g of x function in place of x here. So negative 3 times, and this is the g function, x minus 2 over negative 3. Then add that 2. Do the simplifying. Yep, you get x, which is good. Then we go the other direction, g of f of x. This time we're replacing this x, the x in the g function, with this business, negative 3x plus 2. So negative 3x plus 2 minus 2 all over negative 3. Do the simplifying, gets back to x. That's a check. We did correct work when we found the inverse, because when we compose both ways and simplify, get back to x. Then it was graph the function with its inverse. So in black, folks, I graphed the original function, just chose negative 2 to 2, as I often do, and plugged those in to find y values. Graphed my black line. That's the original function, negative 3x plus 2. To get the inverse function's graph, I switch x and y. So now this becomes my x, this becomes my y. I can't graph that 8, that doesn't fit on my square, but I started here. When x is 5, now y is negative 1. So the blue line is my inverse function, and they are reflections of each other over that y equals x line. Is the inverse, it says, a function? And my answer to this is yes. Okay, there aren't any repeated x's in here, so you don't have to worry about that in the table. In the graph, yep, that passes the vertical line test. Any vertical line that we draw hits the blue graph just one time. All right, ladies and gentlemen, good lesson. We'll talk about it more in school tomorrow.